Welcome to another session of our reading group. Today we're going to look at the relationship between experimental relationships and continuity. So the idea that all the maps in physics have to be continuous in the topology that describes experimental verifiability. So let me put the link as usual in the chat. There we go. And let me share the text. And we can start. Tobias?
Yep. Okay, Chapter 2, Domain Combination and Relationships. We continue our investigation of the fundamental mathematical structures for experimental science by studying what happens when we have more than one experimental domain. We will define experimental relationships between experimental domains, which capture either causal or inference relationships between them. We will see that these correspond to continuous functions in the natural topology. We will take two or more domains and merge all the experimental information that can be gathered through them into a combined domain. We will study how the set of possibilities of the combined domain depends not only on the original domains, but also on the relationships between them. These will also determine the natural topology that can vary from the product topology all the way to the disjoint union topology. We will also show that experimental relationships under suitable conditions can themselves be verified experimentally by constructing the relationship domain for which its possibilities correspond to the possible relationships.
So, dependence and equivalence between domains. The first thing we want to be able to characterize when dealing with more than one domain is when there exists a relationship between them. For example, consider the domains for the temperature and height of a mercury column, or the domains for the temperature and density of water. How do we express in this framework the fact that these domains are connected? We have two ways to define these relationships between domains. The first is in terms of inference. Any measurement on the height of a mercury column is an indirect measurement on its temperature, and any experimental test on the density of water is an indirect experimental test on its temperature. The second is in terms of causes. The height of the mercury column depends on its temperature, and the density of water is a function of its temperature. The main result of this section is to show that these definitions are equivalent, and the dependent domain can be seen as a subdomain of the other. So, suppose d sub x represents the domain for the temperature of a mercury column, while d sub y represents the domain for its height. Since we know that an increase in temperature makes the metal expand, we can infer the temperature of the mercury column by looking at its height. For example, if we verify that the height of the mercury column is between 24 and 25 millimeters, we will be able to infer that the temperature is between 24 and 25 Celsius. That is, given a verifiable statement S sub y, we have another verifiable statement S sub x that is going to be true if and only if the first one is. That is, S of y is equivalent to S of x. Note that the inference is between verifiable statements and not intervals. For example, the verifiable statement, the water density is between 999.8 and 999.9 kilograms per meter cubed, will correspond to the water temperature is between 0 and 0.52 Celsius, or the water temperature is between 7.6 and 9.12 Celsius, as water is most dense at 4 Celsius. The disjunction of verifiable statements is still a verifiable statement, so we are still inferring one verifiable statement from the other. For each verifiable statement in d sub y, we can find a verifiable statement in d sub x that is verified if and only if the first one is. That is, an inference relationship is a map from dy to dx that preserves equivalence.
Okay, so let's look at the diagram at some point here. So the point is that if we take a range of density, this single interval of density, when we reverse map it to the temperature, gives us two intervals of of temperature, but then the union of two open intervals is still an open set. And so that's why open set and verifiable state regions are more important than open intervals by themselves. So we can go to the definition.
Sorry, is it me again?
Mm-hmm.
Okay, definition 2.1. An inference relationship between two experimental domains establishes that testing a verifiable statement in one means testing a verifiable statement in the other. Formally, an inference relationship between two experimental domains dx and dy is a map R from dy to dx such that R of sy is equivalent to sy. In other words, it is an equivalence preserving map between experimental domains.
Okay, so the important thing to note here is we can do that because we have the context, right? So these domains live in the logical context, and it's because they live in the same context that we're able to compare one statement to the other. So defining these objects by themselves without the context in which they live in, you wouldn't be able to know whether any map would be an inference relationship or not. So this is something where you kind of have the problem in math and physics that if you define just two objects, defining the composite, you need more information. It's not just knowing the two objects that you know how to combine them properly in a physical theory. And the point is that the context allows you to do it.
Okay, maybe let me finish the next paragraph. An inference relationship is essentially an injection that preserves equivalence instead of identity. In terms of equality, the two statements, the height of the mercury column is between 24 and 25 millimeters, and the temperature is between 24 and 25 Celsius, are different, but they are the same in terms of equivalence. In this sense, the dependent domain is already contained within the other domain. This means we can define domain inclusion and equivalence based on inference relationships.
So we have a new definition. An experimental domain d sub y is dependent on another experimental domain d sub x, denoted d sub y as a subset of d sub x, if there exists an inference relationship R mapping d sub y into d sub x. Corollary, let d sub x be an experimental domain, and let d sub y be a subset of the statements of d sub x that form an experimental domain, i.e. contains a possibility, certainty, and is closed under finite conjunction and countable disjunction. Then d sub y is a subset of d sub or is dependent on d sub x.
Yeah.
To use the verbiage. Proof. Let iota be a map from d sub y to d sub x, namely the inclusion map. This is an inference relationship since iota of s of y equals s of y, which is equivalent to s of y, and therefore d sub y depends on d sub x.
Right. So that's why we use the notation subset for dependence, because really, in the terms of logical statements, a dependent domain is really a subset.
Makes sense. Yeah. Feels very much like we're like embedding spaces and other spaces with a map R.
Exactly.
Yeah. Or maybe embedding is the wrong word because it can be non-injective, but
no,
yeah.
In terms of the statement, is really injective. So in terms of the open sets, yes, you're exactly embedding the open sets.
Okay.
The point himself, as we'll see, they might collapse into each other, but then the sets really are inside.
Okay, interesting.
And this is where you know it's basically doing this pointless topology where the open sets are actually the main elements, and so the point is just a thing that you create in the different spaces, but they're really not that important.
Yeah, I can see that. That's cool. Yeah, I do feel like there are examples where you could have two open sets that map to the same open set though. Like with the temperature graph, you had like the one interval on like before the bump and the one interval after the bump. And both of those taken as open sets would get mapped onto the same the same open set in the like what
Right. So here the open sets are different, right? And the open sets are here because the points are different. But it's
on
just because the points, a point here is essentially the collapse of 2 points here. Right, a point. If I give you a point in density, that same point in density could correspond to two different points in temperature.
But could you not also have a map that takes statements in like temperature land and maps them onto statements in volume? And that would also be a maybe it wouldn't. No, that
So if you take just this open interval, like this would be a verifiable statement,
mhm.
but when you map it forward, you're getting a different verifiable statement. It's not the same statement because the statement, the density is within this range, corresponds to the union of these two statements.
Okay, so it is an injective map on the open sets.
Right.
Okay, I see now. Thank you.
Right. So like here, basically, because you have more points, you have more open sets.
Interesting. Okay,
And,
so
and,
yes.
and so because you're collapsing points, then you're essentially collapsing open sets, and two different open sets collapse together, they become the same open set here.
Hmm.
And so this has fewer open sets, and so the injection in terms of open sets goes from here to here.
Yeah. Yes.
So
A distraction.
equivalence.
Yes. All right. Definition. Two experimental domains, dx and dy, are equivalent if dx is equivalent or are equivalence noted dx equivalent to dy if dx depends on dy and dy depends on dx. So as a corollary, domain equivalence satisfies the following properties. It's reflexive, symmetric, and transitive, and therefore is an equivalence relationship,
Yeah.
which
The proof we're gonna skip, it's basically just applying the definition. If you want to look it by yourself and have question next time, we can look at. But it's basically you. For the first two is trivial because of the definition, and then the second, the third one, you just have domain like essentially compositions of the map, and you just have to check that they work.
mhm. All right.
Tobias.
It should be evident that we cannot impose inference relationships between any two domains. It's something that the domains allow or not. The domains for the temperature of two different mercury columns are in general not related. Testing the value of one does not tell us anything about the other. Topologies of the two domains, however, are going to be the same because we'll have the same possible values and the same way to experimentally test them. Equivalence between experimental domains is a much stronger relationship than equivalence of the natural topology. It carries enough of the semantic to be able to tell what spaces are truly significantly equivalent.
Let's continue with our example. We can re-express a relationship between domains in terms of causal relationship between the two domains. If x is the value of temperature of the mercury column, i.e. a possibility for dx, and y is the height of the mercury column, i.e. a possibility for dy, then we can write y equals f of x since the height is determined by the temperature. Note that the direction of the causal relationship is the opposite of the inference. X causes Y, and from dy we can infer dx. Chains of events are in terms of possibilities that start with the cause and end with the effect. Chains of inferences are in terms of verifiable statements and start with the result at the end and end with the origin. Right? If X causes Y, if you know Y, you can figure out X. That makes sense, I guess.
The other directions do not work in general. Even if we know the final possibility, we may not be able to reconstruct the initial possibility. If the water density is exactly 999.9 kilograms over meters cubed, the temperature could be either 0.52 or 7.6 Celsius because the density peaks at 4 Celsius. For the same reason, a measurement of the cause is not always equivalent to a measurement of the effect. Verifying that the water temperature is between 0 and 0.52 Celsius will mean that the water density is between 999.8 and 999.9 kilograms over meters cubed, but not the other way around, which is just the example I think we talked about.
Yeah.
Because of the peak in density, the statement about the temperature tells us more, i.e. it is narrower, than the statement about the density, and therefore they are not equivalent. That is, we can learn more about the temperature by measuring it directly than indirectly through the density.
Another important consideration is that in order to be consistent, the function y equals f of x has to be continuous. The general idea is the following. If we say that we can only measure both the temperature and height of Mercury with finite precision, we have to make sure that we can use the causal relationship for inference. Therefore, a finite precision measurement of height will correspond to a finite precision measurement of temperature. This means a small change in height has to correspond to a small change in temperature. The function is continuous.
More precisely, consider the verifiable statement Sy, the height of the mercury column is between 24 and 25 millimeters. The height of the mercury column Y is within the verifiable set U of Sy, which is the interval open from 24 to 25 millimeters. We can then infer that the temperature must be in the reverse image of the possible heights. So inverse F of the set is 24, 25 Celsius. But this means that indirectly, we have experimentally verified that X is in this inverse image. And if dx is really the domain of the verifiable statements for the temperature, then it must contain one that matches the temperature of the mercury column is between 24 and 25 Celsius. In other words, this inverse image must be a set in the topology, and the function is therefore continuous. Here's a footnote. In topology, continuity is defined in terms of the sets in the topology and not in terms of small changes as in analysis. When using the standard topology on real numbers, the two coincide, but not in general.
Okay. Definition 2.6. Let x comma tx and y comma ty be two topological spaces. A continuous function is a map f from x to y such that given any verifiable set uy contained in ty, its reverse image f inverse of uy is a verifiable set in tx. A homeomorphism is a continuous bijective map such that its inverse is also continuous. Definition 2.7, a causal relationship between two experimental domains establishes that determining which possibility is true in the first domain also determines which possibility is true in the second. Formally, a causal relationship between two experimental domains, dx and dy, is a function f from x to y between the possibilities of the respective domains, such that this one is narrower than f of x for all x and x.
Yes, so I want to again note the difference in definition. In the inference relationship, we go from dy to dx, and we have an equivalence through the map. On the other side, we have a map from X to Y, right? So not to the D's, not the domain, but the possibilities, and we go from X to Y instead of Y to X. And what is preserved, it's narrowness, right? So it's not equivalence, it's narrowness. And narrowness you can also think as sort of an implication. If this is true, then this other thing must be true, but not the opposite.
So the X's are possibilities now.
Yes.
Well, isn't that a statement about, isn't that something about statements, not points? Well, it's a theoretical statement. Okay.
Yes.
Okay.
So that's the thing. In our framework, there is no difference between the points and sets, right? Everything is a statement.
Okay. So I can think of it as a singleton kind of.
In that domain, but not in another domain.
Okay.
Right. So so you will have points in Y, right? So this f of x will be a point in Y, but a point in Y is not a point in X.
So if it would
Because
be like an actual like product topology Cartesian product, it would be like a line, the whole line
yes,
in
yeah,
the X. Okay, I see.
right. And see in here again, right? A point in Y corresponds to 2 points in X.
Yeah. Okay,
So
I
the
see.
points basically just come when you have fixed a domain and you say, okay, let's find the narrowest elements, like the narrowest statements that are significant, and those become the points. But then if you introduce a bigger domain, then you have more possibilities, and what the points were become final points.
Yeah. Yeah.
Right. So basically what you consider a point, it depends on not on the context, but depends actually on the domains that you're choosing.
Yeah. Okay,
Right. So
I
if
think
you
no, please finish.
yeah, so if you have values in X and values in Y, where right those values are points in X and points in Y, but then you have a more precise points given by the combination of X and Y.
Yeah. Okay, I think we'll stop at the corollary, right?
Yeah,
All yeah. All causal relationships are continuous functions over the respective natural topologies.
yeah.
Is it
So
worth going through the proof?
I thought we would skip proofs because they become too technical. I think we leave it that if people want to look at them, then we can I'd really like for people to go through the proofs because it's always makes me feel better if other people actually check them and make sure that they're right and come back if there are some mistakes or imprecisions and so on. But we can't, like those things, we can't do it live anyway. It's not that somebody reading the thing live has the time to figure things out. So if somebody wants to do it on their own time and then ask a question during a live, I'm perfectly fine with it. The core of the idea here is again the fact that whatever you're making, when you have statements that are equivalent in X and Y, then if the statements are equivalent and one of them is a verifiable statement, then they must be verifiable statements. So any statement that you have in dy, right? Any statement that you can find in dy that can be expressed in not just dx, but in d bar x in the theoretical domain, then you know that that statement has to be verifiable because the y is verifiable and they are equivalent. That's basically the core. And then what you do is you have to prove that mathematically, and you prove it with disjunctions, but it's not that complicated. It's just technical. And then the other thing that is the other corollary is that the causal relationship between is unique if it exists. You can't have two domains with two different causal relationship, and no, if there is one, there is only one. And then the most important thing is this theorem that inference and causal relationships are equivalent. That is, if dx and dy are two experimental domains, an inference relationship R exists between them if and only if a causal relationship also exists. So the two things are sort of two sides of the same coin, and that is why you can sort of forget about inference relationship and only talk about causal relationships, also because causal relationships are easier to specify because you're only going from points to points, which are significantly fewer than the open sets. Like if you had to give me the map, let's say that you have, again, the functions between temperature and density, right? If you only have to give me the function between the values of temperature and the value of density, you're giving me just this simple map. If you're giving me the map between every open set to every other open set, it becomes a lot bigger. And
So
again, here is the proof.
the thing that makes sense to me is, I guess, if I have the map F, I know, I think you call it how to pull back open sets, right?
Yeah.
And then the other way around works, I guess, because we have like, we know the topology, but we infer the points of the topology anyway, because I guess it's Hausdorff, and we already, like, it's clear how to find the points.
Oh, it's not Hausdorff, but what you know is that the points are defined by a basis.
Okay.
So once you know how sort of to pull back the bases,
Okay.
then you know how to recover the points, and you basically know how to do everything.
Okay, but we infer the points anyway from the topology. So it's clear how to
Yeah.
define the map on the points. Okay, then that makes sense.
Yeah. There is a last corollary. The two experimental domain dx and dy's are equivalent if and only if there exists an homeomorphism between x and y and between the possibilities such that x is now equivalent to f of x. And this is the case, for example, of the steel temperature versus density, because the relationship is linear, and so any, or at least, you know, for some ranges, the relationship is in any way bijective, and therefore now every single open interval on the density become a single open interval on the temperature, and vice versa. Okay.
So, since for each inference relationship we have a causal relationship and vice versa, we will simply use the term experimental relationship to describe the link between the two domains. We should stress that causal relationships and inference relationships are defined on spaces that have, in a sense, a different status in a physical theory. Inference relationships are defined on verifiable statements, on finite precision measurements, which are objects that are directly defined experimentally. In this sense, inferences have a higher status as they are more directly related to experimental verification. However, the map R from dy to dx, or d sub y to d sub x, is overcomplicated and redundant precisely because it maps all possible finite precision measurements from one domain to the other. Conversely, the causal relationship f from x to y is only defined on the possibilities, on the points, and therefore there is no redundancy. However, the possibilities are not verifiable statements in general and are often the product of idealizations. In this sense, causal relationships have a lower status as they are only indirectly defined by experimental verification.
The perfect correspondence between causal and inference relationships, it was is what rescues and justifies the predominant focus on causal relationships to describe experimental relationships. Since studying one is mathematically the same as studying the other, why should we use the more complicated object? Therefore, while the inference relationship is more directly physically meaningful, the causal relationship is a much more convenient object to study and to characterize. That is why, in the end, all relationships will be predominantly defined by a function over the possibilities.
So this is something that happens a lot in physics, even when we define, when we have differentiability and we define forms and all of that. The real objects are on, let's say, finite volume. So if I have to measure mass, I experimentally define a finite mass in a finite volume. I don't measure mass density. I always measure mass in a volume, not mass density at a point. But then if I have to describe, mass distribution, it's much easier to describe it in terms of mass density. Because again, if I had to specify the mass for every different volume, the thing would be redundant. So but it's useful to understand what are the things that are sort of our prime objects and what are the idealization that you need to be able to then define these points, because otherwise you get in trouble.
Yeah. So in some sense, the things we actually can observe are the topologies themselves, but the points make it easy to talk about.
Yeah.
Yeah. All right. We now turn our attention back to domain equivalence. We have seen that two experimental domains, d sub x and d sub y, are equivalent if they consist of equivalent statements, if they allow a one-to-one correspondence that preserves the equivalence of their statements. This implies, for example, that the possibilities are also equivalent, but there's more to it. Suppose we define some type of operation on one domain. For example, on the experimental domain for the temperature of a mercury column, we can define an increase by 1 Celsius. Or in the experimental domain for the amount of gasoline in a tank, we define the sum of two possible amounts. These will correspond to either to operations on the domain, e.g. a function f from d sub x to d sub x, or on its possibilities, like a plus operation from x cross x into x. But by doing so, we are also defining them on all equivalent domains as well. In the end, they are made of equivalent statements. Therefore, we are also defining an increase of the height of the mercury column and the sum of the monetary value of the gasoline. So this is like you can take an operation and like push it forward through.
Yeah, exactly.
Yeah, or is it a pullback?
It's both cases, right?
Okay.
This means that if we capture some physical feature using some mathematical structure in one domain, then all equivalent domains will inherit the same structure. Moreover, the causal relationship is a function that preserves that structure. If the possibilities of one domain form a vector space, then the possibilities of an equivalent domain form a vector space, and the causal relationship is an invertible linear transformation. If the possibilities of one domain form a group, then the possibilities of an equivalent domain form a group, and the causal relationship is an isomorphism. There's a footnote. Domain equivalence is an isomorphism in whatever category. For example, topological space, group, vector space, and so on, used to model the experimental domain. As we'll see much later, this is fundamental since deterministic and reversible evolution means equivalence of the domains describing the past, present, and future states. Therefore, deterministic and reversible motion is not just a one-to-one map.
Okay, so this is, I guess, the theorem associated. Domain equivalence is isomorphism. Let domain Y be equivalent to a domain X. Suppose that the domain X is endowed with some mathematical structure, then domain Y is also endowed with an equivalent structure, and the experimental relationship preserves said structure.
Right. So that's exactly it. You can push everything forward or you pull everything back. If they're equivalent to whatever you have on one side, you can put it on the other side.
So in the case of like Lagrangian mechanics, the relevant structure is some symplectic form, and I'm using that word right. And like the idea is you can like push that forward through time and get a volume preserving.
Yeah. If they are truly equivalent, then let's say that I have two. I have Hamiltonian mechanics. I have symplectic space in the past and the future. If I'm saying that there is some let's say uncertainty or some entropy, let's say, associated with some statement at the beginning, and then I'm saying that the final statement is exactly the equivalent statement at the end, then whatever entropy that was associated to the initial statement has to be associated to the final statement, and therefore things have to remain the same. The entropy has to be preserved.
Like if in theory you can answer all the same questions about something in the future as you could in the past. Like there's no loss or gain of total information in some sense.
Yeah, so if the statements are equivalent, then the whatever other map and structure that you put there cannot be different, because then it wouldn't depend on the statement. It would have to depend on the statement and something else. Right, and so the map that you would put, as you put here, right, these maps clearly depend only on the statements. And so if in the future that f would be different, then it wouldn't depend only on the statements. It would have to depend on something else.
That makes sense.
Right, so for example, it would depend on the statement and the time, right? Because time now would be a property of the map and not a property of, yeah.
Okay. Yeah, we can skip the proof, but
Yeah.
yeah. Note that the converse is not true. Two domains that are endowed with the same mathematical structure are not necessarily equivalent. Consider two similarly constructed thermometers. Their respective experimental domains are not equivalent, since knowing something about one tells us nothing about the other, yet their natural topologies are equivalent because the way we measure the temperatures for both is the same. One way to look at this is that the mathematical structures forget the full equivalence between statements and only look at a particular aspect. Topological spaces capture how the possibilities are distinguished in terms of verifiable statements. Therefore, while the domains for temperature of two different thermometers are not equivalent, their natural topologies are, because the way we characterize all possible measurements is the same, i.e. the value being within some finite precision interval. Similarly, the sigma algebra only cares about what statements can be associated to experimental tests. We'll see that in some cases, abelian groups will capture how distributions can be composed into other distributions, and that non-abelian groups will capture how transformations can be composed into other transformations, and so on.
And that's it for the relationships. Are there questions and comments, even from the chat and people that are following on YouTube?
I get the impression it's going to be much easier for mathematicians to follow what physicists do, just because we now have like the logical context is like something where we can like dump all the complexity. We can at least tell the mathematician like, look, you need the math, you need the context to understand how like these statements all combine. So it is inherently complex, but at least now it's kind of formal, because now they could go ahead and they would be like, oh, this is all category theory. You forgot some structure and all of that. And the complexity of like how all the physics relates to one another is like still there, but we at least have some structure that captures enough of the structure that we still need to prove some things, which I
Yeah.
think is really cool.
Yeah. So the fact that you have the context solves so many things, and the cool thing is that like solve a lot of things conceptually, And the cool thing is that initially I just put it there because of sort of the pushback that I got from mathematicians from the idea that the only undefined objects have to be elements of a set. And so I said, okay, let me just have a whole set where all my objects come from. And then like the cool thing is that all these other things always come from there anyway. And so it's really the logical context that sort of both mathematically and conceptually glues everything together. And it also makes you understand that even conceptually, right, if I have two variables, two physical variables, and I want to know their relationships, I have to assume that there is a bigger context of which these, in which these two variables live, because otherwise, where do I put the relationship between them, right? So at the end of the day, everything works really nicely. It's, yeah. That's how you know when you have good structures, because everything fits into place.
Yeah, I will say I do feel like the physicists still have a job though here because a lot of the complexity, or I feel like there's a lot of complexity in I guess describing the logical context precisely enough that you can start making these statements about it. Like if you could fully just state all the things in your logical context, then then it would be perfectly rigorously defined. But in some sense, a lot of the ones we care about are going to be really, really infinite. Um, and so then there's still the task of being able to characterize it well enough that you can start doing topology to it and that kind of thing. So I feel like this doesn't put the physicists out of business at least.
No, no,
But
no. In fact, no, no. It forces them to describe all the things in a more precise way, so that you know where you are. Okay, so comment from the chat. Yes, it is a relevant question. So causal relationships are relative to which theory you're using. Yes. So you can imagine, for example, let's say that you have a particle and you have all the possible position, a measurement, let's say, of position and momentum, right? And the relationship between all these statements depends, for example, whether you have a classical theory or a quantum theory, right? So if you extend it to statistical objects, which is even better, if you have the space of statistical distribution in classical mechanics and the space of density operators, the statements on the variables, right? Whenever you have a statistical variables and then you go and measure either the expectation or other things, those final statements are all the same. But the type of relationship that you're going to have is going to be different whether underlying you have a classical theory that pulls all these domains together or you have a quantum theory. And so in the simple case that I was saying before is whether you have, if I have a temperature and a density of water, well, there's going to be a relationship whether there is the assumption that that's about the same parts of water, the same amount of water, or it's different amounts. And so this is sort of the general thing. If you just give me the variables by themselves and you don't tell me what is the underlying model that links them together, you don't know what relationship that you can have. Now, mathematician would be able to tell you the space of all the possible relationship that those two things might have. But then, of course, it's the physicists that have to tell you, okay, I have this specific relationship and not the other. So thank you for the question from the chat. And let's see, we have 15 minutes. We can start. I think we're going to be able to at least do the first, at least this first bit we should be able to do. I don't recall who was.
I think it's my turn. In this section, I want to understand what happens when we combine statements from different domains. For example, suppose we have the experimental domain for the pressure of an ideal gas and the experimental domain for its temperature. We can mix and match verifiable statements with conjunction and disjunction, as in the pressure is between 1 and 1.1 kilopascal, and the temperature is between 20 and 21 Celsius, creating a new domain. How can we characterize this combined experimental domain. The main result of this section is that the possibilities of the combined domain depend on how compatible the verifiable statements of the domains are. In particular, if the verifiable statements are independent across domains, e.g., the horizontal and vertical position of an object, then the possibilities of the combined domain will be the Cartesian product of those for the individual domains. On the other hand, if the verifiable statements are incompatible across domains, for example, plant identification and animal identification, then the possibilities for the combined domain will be the disjoint union of the possibilities of the individual domains.
So like a product or a co-product?
Yeah.
Okay, yeah. So suppose that our domain X is the experimental domain generated by the two verifiable statements, the patient is dead and the patient is alive. And the second one, domain Y, is generated by the two statements, the patient is not in a coma and the patient is in a coma. The given verifiable statements also correspond to the possibilities for their respective domains. We can construct the combined domain dx cross dy by taking all possible disjunctions and conjunctions. What are the possibilities? Well, so we have some machinery for this. We know that it's that we just have to consider all the conjunctions of the statements. So we have the patient is alive or the patient is dead, and the patient is in a coma, and the patient is not in a coma. You can kind of make a Punnett square, I guess. So we get these four possibilities: alive and
Yeah.
coma, alive and not coma, dead and coma, dead and not coma. And we note that the third one isn't possible. You can't have a patient that's dead and in a coma. And therefore, the combined domain has three possibilities. And so the possibilities of the combined domain are, in general, the subset of all possible combinations of the possibilities of the domains that we are combining. Yeah, so specifically those that aren't impossible. You take the Cartesian product and you discard all the ones that don't
Yeah.
make sense.
Yes. And so now you have just the definition.
Okay, let dxi be a countable set of experimental domains. The combined experimental domain dx, denoted as this product, is the experimental domain generated from all statements in this collection by finite conjunction and countable disjunction. Okay.
And this is not really a proof, it's more a consistency check. I have to start checking, like changing the proof, what I call the proof after definition in consistency check. I'll make a note. Is this... So the important thing here, I don't know if I say that later, probably not, is we can only do it with a countable set. Because only with a countable set we are guaranteed that the union of the bases will still be countable. Right, so what happens here is that we can check that even if you have countably many bases, you can go and diagonalize all of them, and so you still get a countable sequence. And that's, I think that's the thing, yes.
But
And
so far, we really just throw them all together, right? It's or do we like, is the logical context telling us implicitly what is impossible, and now therefore some of these statements kind of collapsing to just the impossibility?
So you can do this closure, right? This the fact that you can generate this new domain is because you have the overall context, right? If you only had the domain by themselves, you wouldn't know how to take the conjunction between two statements. So the fact that the patient, like that this one is impossible, that the fact that the patient is dead and in a comma it does not exist. It's the overall context that tells you.
Okay,
Right?
so when I combine the domains, I do it like the same, always the same way, but it happens that some of these logical conjunctions, disjunctions, they turn out to be equivalent to the impossibility.
Right. And it's the
Okay.
context that tells you that.
Okay, so like how to combine domains is kind of already built into the context. Well, if you have
Yes.
specified the context, but here I can just like generate all the statements, and then some of them will like automatically combine to or be equivalent to the impossibility. Okay.
Yeah. It's whatever it's gonna be. So the point is that the conjunction of two statements between two different experimental domain exists only in the context. It doesn't exist in the domain itself. And then you have this proposition.
Okay. The possibilities for a combined domain are a subset of the Cartesian product of the possibilities for the individual domains. Formally, let dxi be a countable set of experimental domains and xi be their respective possibilities. Let x be the set of possibilities for the combined domain, dx, that we just defined. Then x are all the statements. This is, I would never remember if it's conjunction or disjunction.
Is the conjunction.
Okay. It's and. Okay. For all sequences
So
that
basically,
pick
you're
one from
taking
each domain, from each possibility.
exactly.
Okay, yeah.
You're taking the disjunction from each element of the possibility, which now this would be the Cartesian product. Like it's all the possible combinations, but you're only taking the ones that are not impossible.
The final result. Okay.
Right, so it's a subset of all the possible combinations.
Yeah.
So
And we
as
use an and
before,
because one thing of each domain has to be true.
yeah,
Okay, yeah, that makes sense.
yes. And so it's the same as here, right? Here we made all the permutation, which were 4 because the domain was 2 and 2. So 2 times 2 is 4. And then we see that one of them is impossible, right? So it's a subset of that. And so this works in any case. And then we have the last two things.
Here I can do this one. So proposition 2.15, let d sub x sub I for I equals 1, I from 1 to infinity be a countable set of incomplete experimental domains, and domain x, their combined experimental domain. Let like a sequence of x with the circle on top. I'm not actually sure how to say that with words, but I guess I'll just call them circle x. Circle x
Yeah, it's an X circle or something like that, yeah.
circle. So the sequence of x circles be the residual possibility of each respective domain. Let x circle equal the conjunction of all of the x circle 1 through infinity. The combined domain x is incomplete if and only if circle x is not equivalent to impossibility, in which case circle x is the residual possibility.
Okay, so this is the awful thing about this possibility that it's true when all the contingent verifiable statement are false, right? So it's basically what remains from having tested everything and you found no possibility. And those domains are called incomplete, if you recall, if there is this residual possibility. And then the point is that if you're combining domains, the only way that the combined domain is incomplete, therefore there exists a residual possibility, is if all the domains are incomplete, and the residual possibility of the combined domain is the conjunction of all the residual possibilities. So you tested all the contingent open and contingent verifiable statements of all the domains. You found none of them to be true or none of them terminate successfully. Then that's the residual possibility of the whole thing. And then the corollary is that the residual possibility of the combined domain is narrower than the ones of the original domains. And if one of the domains is complete, then the combined domain is also complete, because at that point, it's like the residual possibility of one is the impossibility, and therefore you get the impossibility for the whole thing. And again, these are only there to make the coproduct work, and that's it. So since we are basically 5 minutes to 10, we're gonna stop, and next time we basically see the three cases where you have domains that are independent, where you have domains that are dependent, and when you have domains that are incompatibles, and then you see the different cases that you can have and how the possibilities you can combine. And what you will see that the independent domain become the standard topological product, the incompatible domains become the coproduct, and when you have a dependence, it just becomes a function between two topological spaces.
Okay, but all of these use the same definition of how to combine domains. We just look at different logical contexts, right? Either they...
Correct.
Okay, yeah.
Right. So the definition of dependent, independent, and incompatible are going to be relationship between the statements of the domain, and those relationships are defined in the context. So in principle, you could find the two different contexts that have two domains, two experimental domains that look similar to each other, but then when you look at the relationship across, they are different.
Yeah, you could take two domains that make sense, like independently, like and compare classical quantum, right? You could take two observables that, like, I don't know, don't commute in the quantum case, like kind of.
Yeah, even more simply, like even if you just stick yourself in classical mechanics. So if you have a vertical position or horizontal position, right, the domain would still be kind of like the real line, right? And those would be independent because I don't have a constraint between the two. Or we can say, as we said before, the density and temperature of water, those are still real lines by themselves, but when you combine them, you have the relationship. And or you could have, let's see, what's a good example for something. You have to have a variable that is defined on a system, and if you have that variable that is defined, you cannot have the other variable that is defined. There has to be a case that it doesn't come to me right now. But that would be the sort of the incompatible domains. Okay, any other question, perplexity? Let's also see in the chat if anything comes up. I'll give 10 seconds on the chat. Usually there is a delay. Then we close it today since it's 10 o'clock. Thank you all for coming and for listening, and we'll see each other next week. Bye.
Bye.